Okay, so Module 7 is really where we get into the sort of the thick of what statistics is about. And everything else that we've done up to this point has mostly been leading to this. Module 7 is where we start to talk about what we call inference, which is where we use the data that we gather from a sample to make some bigger statements. So let's go ahead and pull up Module 7. I've already done that here. Here we go. So this is the first page, Introduction to Inference in Module 7. So we talk about the statistics, the steps we have in statistics. And here's an example, but we'll go through the steps. If we wanted to know what percentage of U.S. adults support the death penalty, our steps are to, number one, we produce data. So that is, we determine what to measure and collect the data. In this case, they conducted a poll of 1,082 U.S. adults, and they asked each adult the question, do you favor or oppose the death penalty for a person convicted of murder? Then, we summarize the data from the sample. We have 1,082 yeses or nos, or perhaps no opinions for some people. And they found that 65% of people said that they favor the death penalty. And then you would draw a conclusion. So that 65% represents just the sample. So what we need to do, what we're going to be doing in this module and in the next module, is developing the tools to figure out what that 65% says of the sample says about the population. Well, in this case, we're not going to go through how we get it, but basically, in this case, we can be 95% sure that the number for the population is within 3% of that number for the sample. So we can be pretty sure, as it says, we can say with 95% confidence that between 62% and 68% of the population favored the death penalty. So it's possible that the population proportion is outside of that range, but not extremely likely. It's most likely that the population proportion is within that range. So in this picture, our producing data is asking the question. Our exploratory data analysis is sort of what the data said, 65% of our population are in favor of the death penalty. And then we use the tools of probability that we'll learn starting in this module to come with our inference, which is that we can be 95% sure that between 62% and 68% of U.S. adults support the death penalty. Right, so that's kind of the idea of inference. So this is an important line right here. Random samples vary, so inference always deals with uncertainty. And our conclusions almost always involve, as it says in the next sentence, probability statements. Okay, so let's look at another example. Using inference to detect cheating, and this is a real case. So this is, as it says, the details appeared in the magazine Chance. So during an exam at a university in Florida in 1984, the proctor suspected that one student, who we'll call student C, was copying answers from another student, who we will call student C. The proctor accused student C of cheating, and the case went to the university's Supreme Court. At the trial, this is important, the prosecution introduced evidence based on data. So they missed 16 questions. I assume this was multiple choice. And on 13 of those questions, their answers were the same. And then the prosecutor used data to draw an inference based on probability. He asked the question, could 13 of 16 matches be due to chance? Well, the probability of this occurring is very small. So there had to be another explanation besides chance. And the prosecutor here said the explanation was cheating. And based on this evidence, student C was found guilty. Now, there could have been, so we could be pretty sure that it's not due to chance that they had that many matches, but there could be other reasons. Perhaps those wrong answers were the ones that were most obvious. But if you've already got a reason to suspect that one person might have been cheating from someone else, then that unusually high number of matches is probably a good reason to say that cheating probably did in fact occur. So one thing we can do in terms of deciding how likely it is that someone would have that many matches is to do a random simulation. So here's the set of wrong answers for student A and the set of wrong answers for student B, and student C. The green ones are the ones where they matched. So here's some random choices where they selected. I assume there was 4 choices for answers. They randomly selected one of the 3 wrong answers, and then the green is the number that matched. So random set of answers for number 1, where there was 1, 2, 3, 4, 5, 6 matches. For another set of random answers, there was 3. For another set, there was 5. Right? So C and A matched 81% of the time, and for the 3 that we just generated randomly, it was 38%, 19%, and 31%. So those are nowhere close to the 82%. So, and here, in fact, is 100. This is a simulation, 100 random answer sets. And here is 1,025 random answer sets. And you can see, here's the blue line, is the number of matches between student A and student C in reality. This is the number of matches between a random answer set and student A. None of those even gets close to 82%. So that's why we say this is much, much higher than we would expect to see by chance, this number of matches, the 80%. We expect to see, on average, somewhere 30% would be right here. So somewhere between 20 and 40% typically. May see a little bit less than that or a little bit higher than that. It's not very often we'd see more than 50% matches. And we would almost never see, not even one time in 1,000, higher than 70% matches. So we can be pretty sure that the number of matches was not due to chance. So, so we agree that there has to be another explanation besides chance. But this is kind of neat right here. Sorry about that. I'll go back up to that. But could there be another explanation besides cheating? So statistics is supposed to be, as a subject, is supposed to be, we'll call it agnostic. In other words, statistics is just the tool. We can say that we are very certain that this 13 out of 16 matching was not due to chance. There was something else going on. But what was going on? So, as this says, if you don't know the answer to a question on an exam, you rarely guess at random. It is more likely that you will make an educated guess. Some wrong answers might be more logical than others. So this could also explain the large proportion of matches on the wrong answers between the 2 students. So this evidence is not convincing evidence that student C cheated, but we do know that he did not just guess. So, there was a retrial. The student C appealed this case. So now what they did was they took every other student's paper, and then they matched the questions. There was 40 multiple choice, and they counted the number of matches on students' A paper and divided by 40, and they did it for all of the students in class. So here's the graph, And you can see it's a bell curve. It's a nice bell curve, and there's one outlier right over here. And that outlier is our student C. Now this is much more convincing evidence that student C, that either student C copied from A or A copied from C, but their answers were not independent of each other, because we expect to see matches like this in this bell curve, and this is clearly an outlier. So now we have better evidence. The 80%, as it says, 80% of student C's answers match student A's answers. So, and as it says, this time it is harder to argue that student C is not cheating. When we compare him to the rest of the class, this paper had an unusually high number of matches with student A's answers. So that's a pretty neat case, and it kind of gives you the idea behind statistical inference, which is basically statistical inference isn't a judgment of why something happens. It's only a judgment of whether something happens due to chance or whether there must be some explanation other than chance. And in this case, the number of matches is so high that it must be due to something other than chance. So when we compared it to random guessing, it was higher than you would expect by random guessing. It's also higher than you would expect when you look at the matches from other students in the class. So as this says, again, we mentioned this before, statistical inference always involves an argument based on probability. Okay. So let's see here. So we'll go on. So this is sort of an introduction. This is not something that you'll be tested on, but I think it's neat. It gives you the kind of interesting introduction to inference and what we can do with it. So go back and think about what we did in Module 6. Probability is a measure of how likely an event is to occur, and we can make probability statements only about random events. Random here means that the outcome is uncertain in the short run, but has a predictable pattern in the long run. So basically what we do a lot of times is in inferences, we assume something is random, and then as we move forward, we see does it match up with our assumption that it's random. Okay. Let's see here. I think we can go on. Oh, and here's two types of inference. We've talked about these before: estimate a population value or test a claim about a population value. And then here's some different research questions for each type. Make an estimate about the population. What proportion of all U.S. adults support the death penalty? That's categorical. We'd estimate a population proportion. What's the average number of hours that community college students work each week? That's quantitative. And we'd estimate a population mean. So we're almost always either going to be working with a proportion or a mean. And in Module 7, it's going to be proportions. And then you can test a claim about a proportion. Do the majority of community college students qualify for federal student loans? That would be a proportion greater than 1/2. That's what majority means. Has average birth weight in a town decreased from 3,500 grams? Or we could compare to populations. All right, so those are some of the different types of questions we have. All right, so let's now go on to material. Parameters versus statistics. This is important. It's on the quiz, I believe. So basically the idea is, let's see if we can, if it's defined here on this page. Here we go. This is our key right here. A parameter is a number that describes a population. A statistic is a number that we calculate from a sample. And the parameter is usually what we're interested in, and the statistic is what we get. They correspond to each other. So if the parameter, for example, is a proportion, then the statistic is a proportion. The parameter is the proportion from the population. The statistic is the proportion from the sample. If you think back to the first example we looked at, which is what proportion of American adults support the death penalty? Well, the proportion of all adults that support the death penalty is our parameter. That describes our population. We don't know that number. But we did calculate the proportion of the sample, which was 65%, that supports the death penalty. That's a statistic. So the sample proportion was our statistic. The population proportion was the parameter. So when I say something like describe the parameter and the statistic, in that case, I would say the statistic is the proportion of those who were sampled who support the death penalty. The parameter is the proportion of the entire population that supports the death penalty. So that's the difference between a parameter and a statistic. And a parameter is a fixed value, at least at a certain point in time. In other words, at this moment, there is a certain percentage of American adults that support the death penalty. But sample statistics can vary because they come from samples. Depending on which 1,000 people you ask, you're going to get a different percentage who say that they support the death penalty. So parameters are fixed in value, and statistics are variable. So here's some more information. Parameter. When we do inference, the parameter is not known because it is impossible or impractical to gather data from everyone in the population. We make an inference about the population parameter on the basis of the sample statistic. And statistics from samples vary. So the big thing here, statistics allow us to make inference about parameters. Statistics are, and we say statistics are estimates of the parameter. This is from the example above that we didn't go over, but in this case, parameter is a population proportion. For this population of students at a small college, 0.60 are eligible for financial aid. If we didn't know that 0.60, we would say that the parameter is the percentage or proportion of students at that college who are eligible for financial aid. Statistics, sample proportions that vary. And the example, 0.75, 0.65, and 0.375 are all statistics that describe the proportion eligible for financial aid in a sample of 8 students. So those are just specific values, but any group of 8 students would have its own sample proportion. And then we have a parameter population mean. At this small college, the mean amount of financial aid is 1,500. But the statistic would be the sample mean, and here were 3 different sample means. Okay. We also use different notation. You may remember the X bar for the mean for a sample and the S for the standard deviation for a sample. But for a population, we saw these in Module 6. Mu, that's a lowercase Greek letter mu for mean, M for mean. And then a lowercase Greek letter sigma looks a little bit like an O with a tail there. And then for proportion, we use the lowercase p for the population proportion, and then p with a hat for the sample proportion, because it's an estimate. It's sort of like y hat. And then sometimes we refer to the sample statistics as p hat and x bar. Okay. And then there's some notation for the ones above. And it says important comments about notation. Some statistical material, the Greek letter pi represents the population proportion and p represents the sample proportion. The main thing is you just have to understand what it is in your particular version. The reason why some do that is because up here we saw they use Greek letters for the mean, the Greek letter M for the mean, the Greek letter S for standard deviation. So some places you might see the Greek letter pi for the proportion. But we're going to use P for the population proportion and then P hat for the sample proportion. All right, moving forward. All right, so now we're going to look at the sampling distribution, and we're going to talk about the population of part-time college students. And this says females make up 57% of the U.S. college population. Oh. What's frozen? You can't see my screen? Okay, so here we're going to talk about the population of college students, and this says females make up 57%. It says, let's say we predict that 60% of part-time college students are females, so that we think it's a little bit higher for part-time students. We don't have information about the population of part-time college students, so we select a random sample of 25 part-time college students and calculate the proportion of the sample that is female. We don't expect the sample proportion to be exactly 0.60. So how much could the sample proportion vary from 0.60 to make us for us to feel confident in our prediction? To answer this question, what we want to do is understand how much the sample proportions will vary if the parameter actually is 0.60. Okay, so you need to use this applet, but it allows you to go through and do redo a bunch of samples simulate a bunch of samples of 25 students to see what you might typically get. All right, so just as with any other distribution of a single variable, we look at the center, spread, and the shape. We're not going to talk about outliers in this case because we're more interested in the population. All right, what I'm going to do is this video basically simulates doing it a whole bunch of times, and I think I'm going to just fast forward through it. Now what you see, oops, of course, there we go. Oh, come on, you. All right, so you see in the end here, let's see if it, I don't think it's, oh, it's already got bigger. No, and then it went that smaller again. We see here, though, that this is a bell curve in the end, and that's generally what happens, that our sample proportions turn into a bell curve. Not always, but often, and we'll talk about when they do and don't. So let's see. Oh, and go back real quick. It was centered around 0.6, around 60%, just where the population proportion was. So we have a bell-shaped graph centered around the population proportion. So the shape is bell-shaped. The spread is a little harder to describe, but it looks like it's about 10% is the standard deviation. All right. So and here's another one where you have bell-shaped. So let's see here. So it says if we select a random sample of 100 students and the distribution has less variability. I think that must have happened in the second simulation. Yes, so this was from n equals 25, and if you go through this and see the simulation for n equals 100, a larger sample size, what you'll end up with is less variation. And by the law of large numbers, that makes sense, that if you have a larger sample size, your results should be closer to the true results in general. So you're going to have less spread among your samples if you have a larger sample size. All right. Now what we're going to do, we're about to see a formula that describes exactly how that works. Here's another one where you end up with a bell shape. Let's see here. Go through. All right, so here's the key right here. The sampling distribution of sample proportions. This is the sort of the summary of all of what was going on before. So you have a population proportion. We don't know what it is. You take a sample of size n, whatever it might be, and you get a sample proportion. Well, if someone else took a different sample of the same size, they'd get a different sample proportion. They might get the same, but most likely it would be different. And if different people kept taking different samples and getting different sample proportions, eventually what would happen is the mean of all of those would be the population proportion. So the mean of all the sample proportions, the mean of the sampling distribution, is the population proportion. The standard deviation is this big formula here, which isn't as bad as it looks. The p is the population proportion. The 1 minus p is the sort of the reverse. So in this case, the P would represent the 0.60 or 60% that are female, and 1 minus P would be 0.4 or the 40% that are not female, that are male. So we would have these two numbers always add to 1, and you can always just think of them as the two opposite percentages. And then n is the sample size, so you just multiply together and divide. So in this case, if we went, let me pull up the calculator. And show you how you would do that. So in this case, if we were talking about our sample size of 25, we would do, that's my calculator, we would do you can do it all in one line, but you can do 0.4 for the P, 0.6 for the P, times, and then 1 minus P, as I mentioned, is 0.4, and then divide by 25, and hit enter, but that's before I take my square root. The square root is, you have to hit the second key, and the x squared key, and that gives you your square root. And a little trick on the calculator, you could type that number again, but just above the negative key it says A and S. If you hit the second key and then the negative key, it says A and S, and so that takes the square root of the answer I just had. And so about 0.10, and that's about what I estimated it for, about 10% standard deviation. But I could have also done that all on one line. I could have hit square root, and I could have done 0.6 times 0.4 divided by 25, close my parentheses, and I get the same answer. If I increase my sample size to 100, as I mentioned, I should have less variation, so a smaller standard deviation. Divided by 100. And in fact, it's about half. It's about 5% standard deviation. But it should make sense that we have a smaller standard deviation from the formula because I'm divided by the sample size. So if I divide by a bigger sample size, yeah, on the bottom I can't highlight that in, unfortunately, then I'm going to have a smaller standard error. We call it the standard error instead of the standard deviation, and the reason why we call it the standard error is because basically the sample proportion is an estimate of the population proportion. So if it misses it, it's an error, as opposed to deviation is a deviation from the mean, and in this case we're interested in, we're talking about the error of the sample proportion. And then lastly, this is also key. I noted that there was a bell shape. When does that happen? Well, this is when it happens. NP has to be greater than or equal to 10, and then 1 minus P has to be greater than or equal to 10. What do those even mean? Well, it says the expected number of successes and failures. If we look back up here, there was 60% females. If I did 25 students and I multiplied that by 0.60, I would get 15. So what that would mean is that in a sample of size 25, I expect about 15 females, and then 40% or 10 males. They have to add to the 25. So really, you just need to look at the smaller of these two values. All right, and in this case, it would be the expected number of males because 40% is smaller than 60%. So if those two things are true, then basically what that means is you can use the normal model or the bell shape, and I use this mean of P and this standard deviation, the standard error for the standard deviation. All right, so how do we apply that model? Well, here's from our simulation, and this is what we just did. The mathematical model, 25 individuals, the mean is 0.6. We just did this. We got 0.98. Actually, that's wrong. That's supposed to be 0.098. That's a good thing to note. Oh, the square root keys. It's just the x squared key right above it. It says square root. So you just hit the second button there that's red now, and the x squared key, and it gives you a square root. That's all. I hope we're not losing connection. I think my Wi-Fi is still pretty strong. Keep me informed. Oh. Yes, you have your hand raised. Okay, so that's right up here. All right, so basically, to have a bell shape, oh, okay, the sample proportions are going to vary around the population proportion because that's their mean. Okay? How they vary can be described by a bell shape or a normal curve if NP is at least 10 and 1 minus P is at least 10. What does that mean? What is NP? Well, it says the expected number of successes. If we go back up here, we're talking about a population of part-time college students with P equals 0.60 female. What that means is 60% are females. And then the 1 minus P would be 1 minus 0.60 would be 0.40, would be the 40% that are not females. So NP would be the number of females that we would expect to have in a typical sample. So if we had a sample of size 25, the N is 25, the P is 0.60. So if I take my calculator and I do, let's clear the screen. If I do NP would be 25 times 0.60 or just 0.6. So that would mean in a typical sample of 25, I would expect somewhere around 15 females. So it's going to be more, it's going to be less, it could be the same. But on average, that's how many females we would expect per sample of 25. And then in 1 minus 3 would be 0.25 times would be 25 times 0.4. And so there's our, there's 10. Now, so in this case, each of those numbers is at least 10. And so we can use the normal model. You really don't, like I said, you really only need to check the smaller of the two to be sure. But so in a typical sample of 25, on average there'll be 15 males and 15 females and 10 males. Those numbers will vary, but that's the average, the long-term average of samples of size 25. If 16% of the population is female. Okay. So if we go down here, this is basically doing exactly what we just did. Here's the mathematical model. 0.6 is the mean of the sample proportions because that's the population proportion. This is a typo. It's supposed to be 0.098. We did this on the calculator and got 0.098. And then the normal conditions are met. And this is the calculations we just did, the 15 and the 10. So that basically that means we can use the normal distribution to describe this. Let's see here. Then there's some questions. Moving on to the next page. All right. So basically what that means is if we use the normal distribution, we can talk about the things like the empirical rule. We can use z-scores, etc. Let's see here. They didn't go through, I don't think here, the calculation of the mean and the standard deviation, because now we're talking about 100 part-time college students instead of 25. But we did note We did that on the calculator. I'll do it again. If we hit second and the x squared key, we get a square root. And if we do p is 0.6, times 1 minus p is 0.4, divided by 100, that's about 0.05 or about 5%. And so the question here on the screen is, what is the probability that a random sample of 100 part-time college students estimates the proportion within 5%? That is that it's between 55% and 65%. Well, those numbers, if I look at this, and this might be a good time to use my pen. So our mean was, and I do it like this, a mu with a subscript of p hat. That was my population proportion p, which was 0.60. And then our standard error we did with the calculation, that was 0.6 times 0.4 over 100, square root of all of that. And that's about 0.049. And basically it said, what's the probability that it estimates the population mean within 5%? Well, that would mean, what's the probability that the p hat is between 0.55 and 0.65. Well, this is the mean minus the standard error, or standard deviation. And this is the mean plus the standard error. And by the empirical rule, that's 68%. Remember, 68% within one standard deviation, 95% within two standard deviations, 99.7% within three. So we can just use the empirical rule to do that. They do have z-score calculations here, but it's not something that you're going to need. I don't think it's something you'll need to do for the test or the quiz. You may need it for the checkpoint. So let's do that here. Let's see here. The z-score formula in Module 6 was this. It was x minus the mean over the standard deviation. X is just the data value, some data value. Mu is the mean, and sigma is the standard deviation. Okay. But in this example, what happens is x, our data value, it turns into our sample proportion. That's our p hat. The mean is the p, that's up here, p. And the standard deviation is the standard error, which is that formula p hat, p, sorry. P times 1 minus p over n squared of all that. So that's the formula you would use in this module to calculate the z-score of a particular sample proportion. But we are in general going to use the calculator still. All right. So let's see how we can do this problem. We'll do this example, except we'll do it using the calculator rather than the z-score. All right. So it says, let's return to the example of the community college enrollment. In fact, you know what I'm going to do? I think, let's see if it'll let me copy and paste this. I think I might have tried this before. But we'll try it again. Well, that's not bad, actually. I'll make it a little bigger. There we go. Hopefully that's legible on your computer screen. So it says, there we go. So it says, let's return to the example of community college enrollment. Recall that a 2007 report by the Pew Research Center stated that 10% of 3.1 million 18 to 24-year-olds in the United States were enrolled in a community college. Let's again suppose we randomly select 100 young adults in this age group and found that 15% of the sample was enrolled in a community college. Previously, we determined that 15% was a surprising result. Now we want to be more precise. We ask this question, what is the probability that a random sample of this size has 15% or more enrolled in a community college? Well, the first question is, can we even use the normal distribution? Okay. Actually, I don't know why I should just delete that line, but it doesn't matter. All right, so we do our NP, and that N is 100. That's our sample size right there. And then our P is right here, or 15%. So it'd be 100 times 0.15. That equals 15. Well, N1 minus P is just that equals 1 minus NP. I mean, if you distribute the N, that equals N minus the NP. So this is going to be 85. These two numbers here have to add to N. Because everything in the sample has to be a success or a failure. All right. So we got 15 and 85. So those are both more than 10, so we can use the normal distribution. So let's draw our normal distribution here. Our bell curve. And in the middle is our mean, which we said is 0.15. Oh, sorry, I used the wrong number. It's supposed to be 0.10. This is not our P, that's a P hat. Our P is here, or 10%. Sorry about that. The P is the population proportion. So that'd be 10 there and 90. It's still okay. That looks like add ton, add to n. So these are both greater than or equal to 10. So we can use normal. Okay, so it's not 0.15 in the middle. It's our population mean or our population proportion, which is 0.10. And we want to find that it says, what is the probability that a random sample of this size has 15% or more enrolled in a community college? So that's the probability that P hat is greater than or equal to 0.15. That's the probability I want to find. So going back over here to my bell curve, I mark 0.15 on the x-axis. That would be to the right of 0.10. And I want to greater than or equal to means to the right, so I want to find this area over here. Okay. The function on the calculator that finds that is normal CDF. And we'll do it on the calculator in just a minute, but I expect as part of your work that if you used a function like this, you would give it and you would tell you what you plugged into it. The lower bound is the first number you have to plug in. That's 0.15. So that's the left end of this area. The upper bound is the upper end of this area. Well, this curve extends infinitely. So I write infinity, but then I'll show you what we put on the calculator. And then the mean is the 0.10. And then the standard deviation is that formula. It's P, 0.10, times 1 minus P, which would be 0.90. These have to add to 1. Big change from $1. If you take $1 minus 10 cents, that's your 90 cents. And then over your N, which is 100. And you don't actually have to calculate that formula. You can put it right into the normal CDF function. So let me bring up my calculator, show you how you type that in. Okay, so let's clear our screen. The normal CDF is under the vars key, so I hit the second key, and the vars key is actually the DISTR distribution menu. And there it is, number 2. So I hit 2 to choose it. And then the first number I enter in is that 0.15, so 0.15. And then I hit the comma up above the 7. And then for infinity, there's no way to enter an infinity on a calculator. I just use a large number. Like in this case, 5 nines is plenty large. If you had something where the mean was 100,000, then that wouldn't be a large number. So it has to be large relative to what you're doing. Then comma, and then 0.10 or 0.1. You don't have to have the 0 there. And then I'm going to type square root. I'm going to type exactly that square root formula. I'm going to hit second in the x squared key to get the square root symbol. And then 0.10 And I'm just going to do times. You don't need parentheses there. Times 0.90 divided by 100. And then I'm going to close my square root parentheses and close my normal CDF parentheses and hit enter. And so there's the probability right there, 0.0478. 3 decimal places is probably fine, I would say. So 0.048 would be fine as well. So what I'll do is I'll write here that probability is approximately 0.048. Pretty small. What happen? Less than 5% of the time would you get a sample proportion of 15% or higher. Okay. And that's really what you need to do on the quiz. I mean, honestly, at this point, we've covered everything that you would need to do for the quiz. On this, they show you how to do it by using z-scores, but I would expect you to use the calculator, not z-scores. Okay? This sort of assumes you're not using technology. They're doing the lowest common denominator. Some places, FSU statistics classes, you would have to use a z-score. You wouldn't be able to use the TI calculator. All right, this is another example. Again, you should try to use this doing the calculator. I'm not going to do it. I'm going to leave it. Your answer is right there. Let's see. So that's all of that. And then I think you would do, 7.1, the checkpoint. Let's look at 7.2. Right. And 7.2 is really, I don't cover it on the quiz or test, but it's good because it kind of is a preview of what's coming up. All right. We're going to look at 2 types of inference, confidence intervals and hypothesis tests. And we use a confidence interval here, as it says, to estimate a population parameter, like what is the population proportion or what is the population mean. And we use a hypothesis test to test a claim about a population parameter. So, we're going to, as it says, we're going to build on the ideas in topic 7.1 to reason. But we're just going to talk about the logic of inference at this point, not the formal, not all the steps. We'll do the steps in module 8 after the next test. All right, here we go. The National Sleep Foundation, let's look at this example. Sponsors an annual poll. In 2011, the poll found that 43% of Americans between the ages of 13 and 64 say they rarely or never get a good night's sleep on weeknights. That's pretty bad. More than half say they experience a sleep problem every night or almost every night, i.e. snoring, waking in the night, waking up too early, or feeling unrefreshed when they get up in the morning. Are these percentages sample statistics or population parameter? It says it's from a poll, so we can say that these are statistics. They're not from a population. Okay. So it says right here, 60% is not 60% of all Americans, is 60% of our sample. And then when they go further, they say they used a random sample of 1,508 adults, and the margin of error is 2.5 percentage points. Okay, so here's the summary though. Sample is random. Sample size is 1,508. Margin of error is 2.5%. Confidence level is 9.5%. So what that means is we can now take that 60% and add and subtract the 2.5%. That's the margin of error, and that gives us what we call our confidence interval. That means we can be about 95% sure that the percentage for all Americans who have, what did they say, sleep problems every night or almost every night is somewhere within that range of values. 95% confident. So that's basically what there is to a confidence interval. You take your sample proportion and you add and subtract your margin of error. Okay. So what's the connection to the sampling distribution? Basically what we're doing is we're using that bell shape in order to get that margin of error. We're not going to go into much detail just yet. But here's our example though for our female college students. The standard error was 0.049, and in order to get to 95%, we'd have to go 2 standard errors in either direction. That's from the empirical rule. with 68%, 95%, 99.7%. Let's see. So this says we can see that we can be very confident that most samples of this size will have proportions that differ from 0.60 by at most 2 standard errors. So in this case, the margin of error would be about plus or minus 0.098, or plus or minus 10% roughly. And then they do the same thing that they did before. If you had a sample proportion of 57%, then the confidence interval would be 0.472 or 0.668. You add and subtract the 0.098 is where they got those numbers from. All right. Moving forward. So now they do it on a number line. But basically, you take your sample statistic plus or minus your margin of error. In the case of the sample proportion, it's the sample proportion plus or minus 2 standard errors. And if you put that on a number line and put a whole bunch of them, 95% of the time it will capture the population proportion. Okay. So what is the 95% confidence interval? When does it capture it? Basically, what the 95% tells us is that 95% of the time it captures it. So basically, all those times you see that confidence interval on a news story about a poll, 95% of the time, if they're right, that somewhere within that number plus or minus the margin of error, they got the real value that they were targeting. That's what. How confident are we? We're 95% confident. Let's see here. So here's the 95%. Here's the empirical rule right here. I don't know if I did great this time, but there's the 95% right there. So 2 standard deviations or 2 standard errors in this case. That's the connection. So that's why we use the sample proportion plus or minus 2 standard errors. 2 times the standard error. There's an example there. Which you can go through to calculate the standard error. Again, I'm kind of going through this kind of fast, I know, but you can read through it, and it's not on the test. So if you have questions on the OLI checkpoint for this portion, you're welcome to ask them. All right, testing a claim. This is very similar to just that exact same probability we calculated before. Okay, this is test a claim about health insurance coverage. So the Centers for Disease Control estimated in 2010 that 22% of U.S. adults did not have health insurance in 2010. The question is the percentage higher this year? In a hypothesis test, we translate that into a claim about the population. So the claim is the percentage of U.S. adults who do not have health insurance is higher than 22%. To test it, we assume that it isn't higher, that it's still 22%. So it says, but suppose we take 25% of a random sample of 600 U.S. adults, and that's how many, and 25% of them don't have health insurance. What can we conclude? Well, basically what we do, and I'll just do it on the other paper rather than go through this example. Oop, wrong way. That. So what we're going to do is we're going to make this assumption. So we're going to say, okay, well, let's assume that the P is 0.22. We want to find the probability that we would get a P hat of 0.25, the one that was in there, or higher. Well, first thing we need to do, check normality. So we do our N, which was 600, times P of 0.22. That would be, well, 20% is 120, and 12, 132. I assume you'll do that on your calculator. And then 600 times 0.78, that's your 1 minus P. Well, that's going to be much, much bigger. That's going to be 468. So both of these are greater than or equal to 10. So we can use normal model. That means we can use a bell curve. All right, well, here's our mean, our P. This is equal to the mean of our P hats, and then I need to do the standard error, which would be the square root of P times 1 minus P, which would be 0.78, which is what I did over here. Here's my 1 minus P over 600. So I'll have to do that on my calculator. You can't see it behind there, but let's see here. I'm going to do second square root of 0.22 times 0.78 divided by 600. And I get about 0.017. That's accurate enough. So 0.017. All right, so we take our bell curve and we put our mean in the middle, our 0.22, and then our p hat, that's p. Our p hat is somewhere over here, 0.25, and we want to know the probability that p hat is greater than 0.25. So we're looking again at this area to the right. And so again, I would do normal CDF. The lower end is 0.25, the upper end is infinity, the mean is the 0.22, and the standard error is this time I calculated it. I don't have to type it in with a radical. It's 0.17. So I just take my calculator and I do another normal CDF calculation. Alright, so clear, second, and the variables key to bring up my distributions menu. And then I choose number 2, normal CDF, 0.25, missed the 5, 0.25, and then a comma, and then a big number, should do, then another comma, and then a 0.22, comma, and then a 0.017. Close my parentheses, hit enter. So about 0.039 is the probability. Pretty small. So right here, that would be this right up here, 0.039. All right, so what does that tell me? Well, it tells me that if the population proportion hadn't increased, if the proportion of people who have health insurance hasn't increased, then I would get a p hat at least of greater than 0.25, or I should say greater than or equal to, of 0.25 or higher, not very often. Well, is that seldom enough for us to say that it probably wasn't chance that the proportion actually is higher now? Well, that's hard to say. We have to have some sort of cutoff. In statistics, we often use a 5% cutoff. Well, that's something that would happen less than 5% of the time. Okay, so what we could say as sort of a conclusion here is we would see a result of sample proportion as high as 25%, only 3.9% of the time, by chance, if the population proportion is 22%. All right, well, then you have to decide, is that an unusual enough event for you to say that I think that the proportion is actually now higher than 22%? In this case, we might say yes. So might say, therefore, it is likely that the proportion, of uninsured is now higher than 22%. Now, it doesn't mean it's 25%. That's just a value from our sample. We could do a confidence interval if we wanted to estimate it. But it does mean we can be pretty sure that it's higher than 22%. And that's basically, I assume that they're going to get something similar. Yeah, here's their, so they got 0.039 right there, and that's what we got, 0.039. So same value. And then I think they do another example. So sometimes you get more rare events, sometimes you don't. And so if you get something that would happen, say, 15% of the time, then you can say, well, that's not that unusual due to chance. And so I probably can't conclude that my original value was wrong. Let's see. So it says if you're worried about how unusual is unusual enough, we usually say if the probability is less than 5%, that's unusual. So in this case, it was 3.9%. Right, and then we have our wrap up and our checkpoint. So that's the gist. This is an incredibly dense module, but it's very important. 7.1 is the more important one. We're going to be going over the 7.2 stuff again, basically in Module 8. But you got to get 7.1 down. You have to get that the idea that sample proportions vary, and we can describe the variability by using the mean, which is the population proportion, and the standard error, which is their standard deviation, which is that formula. There's the formula right there on the screen without the 2. And they follow a bell curve if you have at least, if NP is greater than or equal to 10 and N1 minus P is greater than or equal to 10. So if we think about the quiz, I can even, let's see, if I bring up the quiz, I'm not going to go over it too much. Actually, let me bring it up through Blackboard now that I think about it. All right. We can talk about how these things relate to what we just did. Here we go, quiz 10. So population sample, those are things we've talked about before. So the parameter is just what we were talking about before. So in this case, is the population proportion. You need to describe that though in words. And then the statistic comes from the sample. You need to describe that in words. And then it says, it gives you the actual percentage, and it asks you to give the mean for the sampling distribution. And then it says what's the standard error, so you use the formula there. And as it says, remember to show your work. Tell why the normal distribution is, we talked about that. And determine the probability that at least 20% of the students in the sample of size 80 have attended the play. So that would be like the example we did where you, in this case, you're trying to find the probability that p hat would be at least 0.20. And then that's if the population proportion was 0.15. So we covered tonight all the stuff we needed in order to do quiz 10, but you just need to put the puzzle pieces together. So that pretty much wraps up what I have to say. Oh, can you please post that? Oh, so somehow I didn't hear your beep that time. Do you have a video of the calculator? I don't, because the steps on a calculator are actually exactly the same as they are for the norms. So, God, I don't know why I didn't hear your beeps those times. I think it might be because you still have the hand up on the thing. Maybe you need to put your, maybe as long as your hand up is up, yeah, there it goes down. I did not hear your beeps go off, and that must have been because of that. So you have to hit the second key before you hit the variables key. But if you watch as far as the steps are exactly the same as they are for the normal CDF. So if you watch the video for that, and that is, oops, I went too far. Sorry, this is, if you watch the video for that one, and I can pull it up momentarily, that's going to have the, and the normal CDF is really more the one that we're going to be concerned with. So if you have the video, if you watch the video for that, it's also applies to this. It's not, the steps you do aren't any different. So I assume then that you did end up redoing the calculation and getting the same thing there in the end. Okay, good. Do you have any other questions before we wrap up? Like I said, I know this was a very dense set of materials. Yes. So if you feel free. Fortunately, I mean, you have a week and a half if you need it to wrap things up, and you can send in questions over time. But I won't do the Q&A question until after we're back from spring break on that Monday. And because that's a test week, I'll probably do a test review session on that Tuesday rather than Thursday would be worthless because the test, you'd have to have it done. But I'll do it that Tuesday night. I think that's the 18th, Tuesday the 18th. All right. Well, have a good evening, Gypsy. Thanks for coming. Your classmates will thank you when I post the video. And you have a good evening.